Hello and welcome, dear students. In today's lecture, we are going to learn about coastal geomorphology, landforms and processes. Before we begin, let me ask you to think about something simple. Have you ever noticed that a beach you visited a few years ago looks different today, wider, narrower, or changed completely? This is because coastlines are not static boundaries, they are the active zones where atmosphere, land, and oceans continuously meet and respond to each other. Coastal regions respond very quickly to changes in wave energy, sediment supply, sea level, or even human interference. And even small change in any of these can lead to major changes in the coastal regions. In this lecture, we will not consider coastlines as static features on map. Instead, we will look at them as dynamic systems shaped by ongoing processes and controlled by natural forces. The understanding of coastal geomorphology helps us explain why certain landforms exist, how they evolve over time, and why are some coasts more prone to erosion, flooding, and sea level rise than others. With this perspective in background, let us now start our lecture. First, oceans and coasts. We know the Earth system is substantially affected by the oceans. Ocean water acts as a storehouse of heat, energy to fuel hurricanes, and is constantly sculpting the boundaries of the continents. The oceans and the lithosphere meet at the coast. The coast consists of sediments of terraneous origin brought by rivers and from the erosion of the coastal rocks by ocean waters. The climate exerts a primary control on the production and supply of sediments both from the river catchments as well as the sediments produced from the coastal and shallow marine settings. Coasts encompass a diverse range of environments including beaches, deltas, estuaries, tidal inlets, tidal flats, stranded plains, lagoons, barrier islands, and rocky cliffs. The landforms of the coast are fashioned by weathering, waves, tides, erosion, transport, and deposition of sediments. Besides, the landforms of the coast are also influenced by the geology of the coast, sea level changes, and tectonic activity and human activity as well. The processes, for example, physical, chemical, and biological actions shaping the coasts are known as coastal processes. Now we will discuss these coastal processes. First, weathering. Coastal environments experience similar weathering processes as that of land, but the action of seawater and wetting and drying of rocks and sediments due to tides intensifies it. For example, on limestone coasts, localized chemical solution occurs mainly in rock pools, where seawater acidity can vary. Salt weathering occurs where coastal rocks absorb salt water and spray, particularly in the intertidal zone. Biological erosion, that means the breakdown of rocks by organisms, is more important in coasts where wave energy is low. Rocks are eroded chemically through chemical secretion, mechanically through rasping, or both. Cyanobacteria and algae are the major bioeroders, while many animals like chitons, gastropods, and echinoids weaken the rock surface chemically and through their teeth and hard body parts. While weathering weakens coastal rocks in situ, the actual removal and shaping of this material is largely accomplished by waves, which acts as the most energetic agent of coastal erosion. The erosion through wave action depends upon the wave energy, structure, and composition of the coastal rocks, location of the rocks or rock cliff with respect to the shore. For situations where rock cliffs are located in the deep water, the waves cause the least erosion as the waves strike without breaking. In contrast, more erosion and transportation of material occurs where waves feel the ground, increase in height, break and rush up against the shore. Although waves dominate short-term erosion and sediment movement, Their effectiveness is strongly modified by tides, which control water levels, exposure of the shore, and the vertical range over which erosion and depositions operate. Tides follow a regular cycle called as tidal cycle, consisting of two high and two low tides, occurring approximately every 24 hours and 50 minutes. The diurnal rise and fall of the tides impacts the sediment movement along the coasts, leading to the formation of such features as tidal sandbars, salt marshes, and estuarine deposits. In addition to tides, the horizontal movement of seawater in the form of currents plays a crucial role in coastal erosion and deposition. Currents are ocean waters in motion driven by wind, tides, density, and temperature differences. Coastal currents are influenced by the shape and configuration of the coasts. For example, bays and headlands and other features can deflect the currents, leading to the erosion or deposition of sediments along the coast. Tidal currents are especially powerful along estuaries, small inlets, and in areas with significant tidal range. Climate change also affects currents, making them sluggish or increase in their velocity. Now the question arises, what is the principal mechanism by which coastal erosion occurs? We know that coastal erosion occurs because waves, tides, and currents constantly strike, move along, and strike at an angle and take material away from the shore. These forces shape the coastlines over time, sometimes very slowly and sometimes very fast, especially during stormy conditions like typhoons and hurricanes. These coastal processes operate through several principal mechanisms. We will now look at each of these, starting with hydraulic action. Hydraulic action is a key process in erosion of coasts, carried out when powerful waves strike the coastline and toss the water into cracks, faults, joints, and weak zones in the rocks. The force of water makes this structural weakness weaker and dislodges the pieces and chunks of rocks from the coastal rocks. The hydraulic action is most powerful where high energy waves strike vertical cliffs or where soft and easily erodible rocks are present. In these settings, waves can even detach and transport very large blocks with a weight of up to several tons. With the passage of time, this process creates various coastal features such as cliffs, sea caves, wave-cut notches, wave-cut platforms, sea stacks, etc. While hydraulic action loosens and dislodges rocks, abrasion becomes effective when the broken rock fragments are used by waves to further wear down the coast. During abrasion, the broken rock fragments scrape, grind, and abrade the coastal rock slowly. Since waves batter against the coast constantly, these particles also keep striking the coast, slowly and eroding the rocks. This continuous hammering of rock fragments of various sizes against the coast is called artillery action of the sea. The abrasion depends on the type of rocks. For example, soft rocks like limestone, shale erode very fast compared to hard rocks like basalt and granite. Besides, the sediment size and velocity of waves also determine the coastal abrasion. For example, abrasion is more prevalent where waves are powerful and laden with bigger rock fragments. As the rock fragments are repeatedly moved by waves, they collide with one another, giving rise to the process known as attrition. This process can be seen clearly in the surf zones and in those locations where strong waves move sediments. As waves move, rock particles constantly grind and collide. These recurrent impacts cause them to break, chip, and wear down, gradually shrink their size. The energy of waves also plays an important role, with high energy waves increasing the frequency of particle collision, speeding up this process. Attrition plays an important role in creating sand and fine sediments of beaches and coasts. This process helps us in the formation of offshore bars, dunes, because these fine rock particles easily migrate to new locations due to wind and waves. In addition to these mechanical processes, coastal erosion also occurs through chemical action known as corrosion. It is also called solution or chemical action and occurs through agents like salt, acids, moisture. Calcareous rocks, especially limestones, are eroded through corrosion, and this process is most prevalent in coastal waters having a high concentration of dissolved salts such as chloride ions. Various factors like composition of rocks, time of the exposure of rocks to seawater, frequency of wetting and drying all determine the effectiveness of corrosion. Having understood the principal mechanism of coastal erosion, we can now look at the coastal landforms they create. These landforms are classified into two main types, erosional and depositional landforms. Let us begin with one of the most common landforms along the coasts, that is the sea cliff. Sea cliffs are precipitous rocky slopes rising almost vertically from the sea, occurring along 80% of the ocean edges. The steep gradient of the sea cliffs relies on the type of rock, structures present in the rocks, orientation of rock strata, and the nature of the wave action at the cliff base. Hydraulic action and abrasion are the main processes forming the sea cliff. As the waves hit the base of the cliff, an indentation known as wave cut notch is formed. This notch gradually grows inland, rendering the upper portion of the cliff fragile and hanging. Finally, as the notch widens, the hanging rocks lose support and fall. This collapse or fall retreats the cliff landwards over time. The pace at which the cliff retreats is determined by factors like rock type, structure, and composition of the rocks, cliff height, cliff aspect, energy of waves, topography of offshore, and how fast the fallen material is removed by sea waves. The cliffs of Moher, Ireland, are famous for their fascinating landscape. The retreat of the cliff through erosion along the wave-cut notch leads to the formation of rocky wave-cut platforms known as abrasion ramps. The speed with which the notch grows and the abrasion ramp forms depends on rock composition and hardness, the power of waves striking the cliff base, and the rock material available to the waves. The abrasion ramp is almost smooth and has a slope of almost 1 degree towards the sea. Marine potholes are also observed on the abrasion ramps, formed through the swirling action of rock fragments associated with the action of waves. In case of sea level rise or fall, for example during interglacial and glacial cycles, the abrasion ramp acts as a marker for the former sea levels, and it is slope for the vertical tectonic moments. On coasts where waves repeatedly hit the cliff, zones of weakness such as cracks or faults gradually widen, eventually forming the sea caves. Quite often sea caves form in carbonate lithology, as these lithologies are weak and are easily eroded by solution processes. Sea caves are not permanent features, but as the dissolution process continues, it makes the roof of the cave thin, which ultimately collapses, forming a mini bay called as Cove in Scotland. Sometimes it may develop in the roof of the sea cave as it grows in size due to continuous wave action. The powerful waves create water and air pressure, which becomes very strong inside the confines of the cave. Over time, this pressure cracks open the roof of the cave, creating a vertical opening through which jets of spray emerge. These sprays often match with arriving storms and waves, making the blowholes remarkable coastal features. If a sea cave continues to be eroded all the way through a rocky headland, it may eventually form a natural bridge known as sea arch. If the rocks are resistant, the arch survives for a long period of time. If the arch is very long compared to its width at the entrance, then it is known as sea tunnel. Some well-known examples of sea arches around the world are coastal arches in Baja California, Mexico. The Azure window in Malta collapsed in 2017. Durdle Door in England, the 12 Apostle areas in Australia, Cabo da Roca in Portugal. Over time, the roof of the sea arch may collapse due to the continued erosion and weathering, leaving a vertical column of rock isolated from the coast. This feature is called as a sea stack. The stacks are peculiar landforms in cliff-dominated coasts. Old Man of High is a towering 140-meter stack carved in the old red sandstone on the western coast of the Orkney Island, Scotland. So far we have seen how erosion shapes the coastlines. Now let us look at depositional landforms, which are formed when sediments carried by waves, tides, and currents are deposited along the shore. One of the most common depositional landforms along the coast is beaches. The favorable conditions for the formation of a beach are calm sea and gentle winds, which allow sediments to accumulate and erode away. Some beaches are wide and spread across the shore, others are just like ridges with a steep slope towards land and a gentle side seawards. The material that forms beaches is supplied by the erosion of the coastal rocks, rivers, storm waves, landslides, and mass wasting and reworking of previous beaches. In terms of size, beaches can vary from a few meters to several kilometers wide. At middle and high latitude regions, the beaches composed of pebbles are more prevalent because the coarse glacial and periglacial sediments supply the pebbly material. Conversely, on the coasts of tropical regions where glaciers are most absent, sandy beaches are common mainly because fine sediments are carried by rivers and supplied by cliff erosion. As waves and currents continue to move and deposit sediments, a narrow and long low relief deposit of sand, mud, or shingle forms off the shore. This feature typically runs parallel to the shoreline is known as a bar. Bars are created by waves and currents and can be connected to the land or may be located slightly away from the shore. Bars connecting the two headlands are known as bay bars. When bars are permanently submerged under the water, they are called submerged bars. And when the rise and fall of tides covers and exposes them as tidal bars. When bars are large and significantly prominent, they are referred to as barriers. A bar running parallel to the coast without touching it is known as a longshore bar or offshore bar. Spit is the most prevalent bar type and forms when the bar becomes attached to the land on one side and the other side extends out towards the sea. Longshore drifts transporting sediments parallel to the coast feed the spits. If the spit is curved or bent towards the land due to the action of strong waves, the bar takes a curved shape which is known as hook or hooked spit. In circumstances when the hook's growth continues outward and landward, it forms a loop and encloses an island. Such bars are known as looped bars. Owing to continuous growth, spits can sometimes connect two headlands, two islands, or a headland and an island. Such spits are known as connecting bars. Tambolo is a striking coastal bar that connects the island with the mainland. Winged headlands form when bars rich in cobbles or pebbles form on the both sides. Next, let us look at spits. Spits are narrow finger-like extensions of sand or gravel that project from the coast into water. Spits and bars act as speed breakers for the waves and tides, making the rear side of the sea comparatively calmer, which allows the finer sediments to settle down, leading to the formation of coastal wetlands. The areas are actually saline, low relief, flat, waterlogged, and marshy with mangroves as the dominant vegetation. Sundarbans in West Bengal, India is one of the largest mangrove environments in the world. Similar low relief flats in coastal areas of dry tropical regions are called salt flats or sabkhas. These salt flats, owing to the intense evaporation, are barren, dry, salt crusted, unlike the coastal wetlands in humid regions. When onshore winds pick up the loose sand from the beaches and deposit it at the edges protected from the waves and currents, dunes are formed. These act as barriers for high tides, big waves, and storm surges, and act as storehouse of sands for rebuilding beaches after storms. Looking similar to desert dunes, coastal dunes are characterized by a dune ridge just at the rear of the beach. Prevailing westerly dominated coasts are associated with large dunes, and coasts exposed to trade winds possess generally smaller dunes. Further that, coastal dunes are smaller and fewer in tropical and polar regions. Wind strength, coast shape, wave energy, sand supply, and vegetation all play an important role in the shape and size of dunes. In addition to sedimentary depositional features, some coastal landforms are also built biologically by marine organisms like coral reefs and atolls. A coral reef is a hard ridge built near the shore by skeletal remains of coral polyp over generations, with the top covered by living corals. An atoll is a coral reef, usually ring-shaped, surrounding a volcanic island which slowly sinks while the reef keeps on growing upward. With the passage of time, the island sinks below the sea level and only the circular reef and atoll remains. The largest coral reef is the Great Barrier Reef of east coast of Australia, with a length of over 2,600 kilometers. The landforms such as terraces, wave-cut notches, and platforms carved on the reefs, as well as the distribution of weak and resistant reef-forming species, act as markers for dynamic sea level changes. This is all for today's lecture. I hope you enjoyed it. Thank you very much.